Hello everyone. Today we discuss fifth rule to find integrating factor. What is differentiation of x raised to km into y raised to kn? Here k is km and n, these are numbers. Using product rule we get this as km into x raised to km minus 1 y raised to kn. We are differentiating the first term x raised to km, so here it is dx and plus kn y raised to kn minus 1 x raised to km dy. Here we can take some terms common, say k into x raised to km minus 1 y raised to kn minus 1. And we have m y dx plus n x dy. Now we know that the term m into y dx plus n into x dy is not exact. This term is not exact. So if we have simply y dx plus x dy, then we know that it is d of x into y. But here we have m into y dx plus n into x dy. However, the left hand side d of x raised to km y raised to kn suggests that if we multiply by some factor, then we may have exact equation. So if we have equation of the form m into y dx plus n into x dy, then simply multiply it by k into x raised to km minus 1 into y raised to kn minus 1, or this k, constant k, may be left and we can just multiply by x raised to km minus 1 into y raised to kn minus 1 and produce exact differential. Another thing is we may have equation of the form x raised to alpha y raised to beta into my dx plus nx dy. So how to find integrating factor in this case? We know that the equation of this form k in x raised to km minus 1 y raised to kn minus 1 into my dx plus nx dy is exact. So we convert this equation by multiplying by suitable factor. Say here we have to multiply by first term is x raised to alpha, but we want x raised to km minus 1. So we multiply by x raised to km minus 1, and we don't want this alpha, so we subtract this, so minus alpha. Similarly, we write y raised to kn minus 1 and we don't want this beta, so we subtract. minus beta. So our equation will be converted into exact differential, and this is nothing but integrating factor. This is our integrating factor. So fifth rule is for the equation x raised to alpha y raised to beta into my dx plus nx dy equal to 0. The integrating factor is x raised to k m minus 1 minus alpha into y raised to kn minus 1 minus beta. Now we consider general case. General cases, we have two such factors. So our equation is of the form. So consider differential equation of the form x raised to alpha y raised to beta into m y dx plus nx dy. This is first factor, and there is another factor plus x raised to alpha 1 y raised to beta 1 into m1 y dx plus n1 x dy equal to 0. Here we have two factors. So we will have one integrating factor to make exact differential of first part, and another integrating factor which will make second part exact. So we have to combine these two and get a single integrating factor. So the factor. So for first part, we will have x raised to k m minus 1 minus alpha y raised to kn minus 1 minus beta. This factor will make the first part, that is x raised to alpha y raised to beta into my dx plus ny nx dy. exact. Similarly, the factor x raised to now k and k1 are unknown. So here we take k1 x raised to k1 m1 minus 1 minus alpha 1 y raised to k1 n1 minus 1 minus beta 1. Okay, so this will make x raised to alpha 1 y raised to beta 1 into m1 y dx plus n1 x dy exact. Here k1 and k are arbitrary, any two numbers. We will select the common value so that we get a single integrating factor. Here we have two integrating factors. So how to find single integrating factor? So we equate these two powers. Say here for first integrating factor power is km minus 1 minus alpha. For second integrating factor the power of x is k1 m1 minus 1 minus alpha 1. So we equate these two factors. The known things are m, m1, alpha, alpha 1, k and k1 are unknown. Similarly, in second, that is where we consider power of y, it is kn minus 1 minus beta, and for second part it is k1 n1 minus 1 minus beta 1. We equate these two, where n, n1, beta, beta 1, these are known terms. So we solve these two equations. So our equation now is k m minus 1 minus alpha is same as k1 m1 minus 1 minus alpha 1, and second equation is kn minus 1 minus beta is equal to k1 n1 minus 1 minus beta 1. So when we solve this for k and k1, solve this for k and k1 to find common integrating factor. We solve one example of this kind. Example is solve y cube minus 2x square y into dx plus 2xy square minus x cube dy equal to 0. We rearrange this equation. So we take first terms together, rearranging, we get y cube dx plus 2xy square dy. We have taken this term and this term together. So this is first part. Second part is minus n we may take common, minus 2x square y dx plus x cube dy equal to 0. Now we compare this with standard equation. So comparing with our standard equation is, before that we simplify one more step. So we need equation of the form my dx plus nx dy. So this here we take y square common. So it is y square into y dx plus 2 times x dy. From second factor we take, so here we need some constant into y dx. So we take x square common, so that we get minus x square into 2y dx plus x dy equal to 0. Now we compare with standard form. Comparing with x raised to alpha y raised to beta my dx plus nx dy plus x raised to alpha 1 y raised to beta 1 into m1 y dx plus n1 x dy equal to 0. So now we find the unknown things. So we get our alpha is 0, beta is 2. Alpha equal to 0, beta equal to 2. Then my dx, m is 1. nx dy, our n is 2. Then from second term we have alpha 1 equal to 2, beta 1 is 0 because in the second there is no y term. Okay. Now in bracket there is 2 IDs but minus sign is outside. We can skip minus sign, that will not affect integrating factor. But let us take m1 to be minus 2. n1 is minus 1. Similarly, n1 is minus 1. So we found all the terms. Now we have to solve equation to solve km minus 1 minus alpha equal to k1 m1 minus alpha 1 minus 1, and second equation is kn minus 1 minus beta equal to k1 n1 minus 1 minus beta 1. So we solve this for k and k1. So first equation is m equal to 1, so it is k minus 1, alpha is 0 equal to second equation k1 m1. m1 is minus 2, so minus 2 k1. Alpha 1 is 2, so minus 2 minus 1, it is minus 3. Similarly, second equation is kn minus 1. n is 2, so 2k minus 1 minus beta. Beta is 2, so minus 1 minus 2, it is minus 3 equal to k1 n1. n1 is minus 1, so minus k1 minus 1 minus beta 1. Beta 1 is 0, so simply it is minus 1. We simplify this equation. So it is k plus 2k1 equal to 1 minus 3, that is minus 2, and second equation is 2k plus k1 equal to 3 minus 1, that is 2. And we solve this for k and k1. So with routine algebra, this will provide the values of k and k1. This implies k1 is minus 2 and k is 2. Therefore, integrating factor is in such case, either we can take integrating factor as x raised to k1 m1 minus 1 minus alpha 1 into y raised to k1 n1 minus 1 minus beta 1, or it may be x raised to k m minus 1 minus alpha into y raised to kn minus 1 minus beta, because these two things will be same. So let us see. Integrating factor is x raised to km minus 1 minus alpha y raised to kn minus 1 minus beta, that is nothing but km minus 1 minus alpha. K is 2, m is 1, so it is 2 minus 1, that is 1 minus alpha. So it is simply x. Similarly, kn minus 1 minus beta, it is k is 2, n is again 2, so it is 4 minus 1, 3 kn minus beta, kn minus 1 minus beta. So k is 2, n is again 2, so it is 4 minus beta. 4 minus 2 is minus 4 minus 2 is 2, minus 1 it is 1, so it is again y. So this is our integrating factor. You can also check that this is same as x raised to k1 m1 minus 1 minus alpha 1 y raised to k1 n1 minus 1 minus beta 1. So this is our integrating factor. So multiplying integrating factor xy to given dE, we get, so our dE is this one, y square into y dx plus 2x dy minus x square 2y dx plus x dy. We multiply this equation throughout by xy, so it will be x into y cube into y dx plus 2x dy. Similarly, we multiply second factor by xy, it is minus, it was x square into 2y dx plus x dy. So multiplication by xy, it will be x cube y into 2y dx plus x dy equal to 0. Now we this equation is exact and we can solve using any of the method. We try to simplify this equation. So this is nothing but x into y raised to 4 dx plus 2 times x square y cube dy. This is first part, and second part is minus 2x cube y square dx plus x raised to 4 y dy equal to 0. Now the first is total exact differential of some term. Okay, so if we check differentiation of x raised to 2 into y raised to 4, then it will be 2 times. Okay, so important term here is x raised to 2 y raised to 4. Its differential is 2 times x y raised to 4 dx. We are differentiating the first term x square, and now using product rule second term plus 4 times x square y cube dy. Now you can check the first term in our equation. So it is, yeah, there should be 2 here. I missed 2. So in the first term here we should have Now if we multiply for and divide by 2 to first part, then we get exact differential. Similarly, in the second, we have 2 times x cube y square dx plus x raised to 4y dy, which is in the form of differential of x raised to 4 y square. So d of x raised to 4 y square is 4 x cube y square dx plus differential of y square, it is 2 times y dy into x raised to 4. So 2 times x raised to 4 y dy. Now check the second again. Again we can see it is in the form of differential of x raised to 4 y square. So we multiply our equation 1 and multiply and divide by 2, so that it is 1/2 into d of x square y raised to 4 minus 1/2 d of x raised to 4 y square equal to 0, and which is easy to integrate. So 1/2 can be cancelled by multiplying throughout by 2. So it is d of x square y raised to 4 minus x raised to 4 y square equal to 0, and so we have x square y raised to 4 minus x raised to 4 y square equal to constant. This is required solution of given differential equation. Thank you.